Engineers at Sandia National Laboratories have designed and developed the world's first continuously recirculating high-temperature falling particle receiver for concentrating solar power.
So conventional receivers are comprised of tubes, panels of tubes, through which you have a heat transfer fluid that flows to absorb the heat of the concentrated sunlight. So this is an example of a tubular panel. And you can see here you've got a set of tubes through which either water or molten salt is flowing. Now the problem is you have the sunlight heating the tubes first. Then you have to transfer the heat through the tube walls to the heat transfer fluid. And that's additional resistance. And so you have limits as to how much solar flux you can put on these tubes. So in contrast, by heating particles directly without using tubes to contain the particles, we can drop the particles through the receiver, and by heating the particles directly, we can get to much higher concentrations. We can apply very high concentrations, well over 1,000 suns or 1,000 times the sun's irradiance. And we can have very efficient heating of these particles, and they can get very hot. These ceramic particles can get, in theory, well over 1,000 degrees Celsius. And the really neat thing about these particles is that they're currently used in the oil and gas industry. They're called proppants. They're used in hydraulic fracturing, and they prop open the fractures. So when they blow open the fractures to get the oil and gas, they'll inject these particles to keep those fractures open. So we're using these commercially available particles for now a renewable energy technology for concentrating solar power.
The falling particle receiver would enable cheap, efficient energy storage for 24/7 electricity production and is capable of being retrofitted on existing concentrating solar power systems. Sandia's 1 megawatt prototype has been featured in several magazines and journals like R&D Magazine, Science Daily, and Renewable Energy World.
And so the falling particle receiver is a fairly simple concept. It uses a particle elevator to lift particles up to a top hopper, and in the top hopper the particles sit until they're ready to fall through the receiver, which has the solar flux from our heliostat field. And so when they fall through the receiver, they fall through and absorb that solar input, and then they fall into a bottom hopper, which can do two things. It can either store the particles, and so in doing that you store that thermal efficiency in order to generate heat or electricity at different times of the day when you don't have solar input, or you can take those particles and recirculate them through the system to heat them up to even higher temperatures.
So what you're looking at here is a mock-up that we created of the falling particle receiver, intended to look at the flow of the particles and what impacts the flow or the hydraulics of the particles. So we looked at the impact of wind on air curtains, different size of particles, various parameters that influence how the particle flows through the receiver. And so what you're looking at here is the opening. This is where all of the sunlight, all of the concentrated sunlight would shine through and illuminate the particles. I can open up this slot and particles will then fall through, and you'll see a curtain of particles falling down into the cavity receiver where they would be illuminated and heated. You can see the particles are flowing in a unique sort of zigzag pattern. We're currently doing some research on different particle release patterns to increase the light trapping and efficiency of this receiver system.
The falling particle receiver opens up new application possibilities, including thermochemical storage, solar fields, industrial process heat, and water treatment to address our global energy and water needs. And the goal of achieving 90% thermal efficiency addresses the Department of Energy's Sunshot initiative to make solar energy cost competitive with other forms of electricity.
The particles are going to allow us to charge the storage to much higher temperatures than we can now. That means that we can then have higher temperatures to the turbine, therefore higher efficiencies and therefore lower costs. Now, if we want to have very high efficiency storage, we're going to need to have high efficiency receivers to be able to charge that storage. and particle receivers look like one of the ways of the future.
This falling particle receiver enables the ability to generate renewable electricity with storage, round-the-clock production of electricity cheaply and efficiently without the need for very expensive battery components.